Okay. So I hope everyone's doing well. I have okay. I hope everyone's doing well. I hope everyone thought that the first exam makeup was appropriate. Not too bad. Um, Moving forward, the second and third exam will be very similar to the first that 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 assignment, I guess you could call it. So we are in the midst of grading them, and so far the grades have been rather good. Some of them have already been posted, some of them haven't. If you get your grade and you would like to talk about it, I'll be more than happy to talk about it. And we could adjust your grade accordingly if you convinced me of you know that you deserve something you think you didn't get. I'll be more than happy to take the time to talk to you about it. Just let me know. The second exam slash assignments, I guess we all Dr. Clayton is looking at the 19th to the 24th for it to be assigned. So next weekend, basically. Um, I've seen it, and the content that we've been covering in recitations tracks rather nicely with it. So I hope that that is useful. I will post my recitations on YouTube. I haven't forgotten about that. I just haven't done that yet. But if there's any questions about that, we can get started on the topic for today. Do you know if the final will cover more than one day? Yeah, that's a good question. That's a great question, actually. I don't know. Because some of us have 4 exams counting this course. Yeah, so I think it's going to be, my understanding is it's going to be kind of like you're going to have like a weekend to do it. You know, because originally we were only going to give you 24 hours to do the assignment, and I was like, no, you should really give them more time. So like the Thursday to Tuesday, I think is good for people. So if you you can plan your schedule, and I think that's what we're going to do for the final. I don't understand, like it doesn't make sense for us to constrict it that way. So I'll make a point of asking him about it, but I don't see any reason why it would just be one day. Also because like everyone's exam schedule is different, so like if you're in different classes, whatever, I don't know. So I'm pretty sure it's going to be multiple days, but if it's not, I'll let you know. Okay. So yeah, see, Storybook is weird. I don't understand why they do that. I don't get it. When I went to undergrad, like we had the exam in the class. It was like you just take it when you had the, okay, whatever. Anyway, yeah, well, I mean, we're also like, we're trying to make your lives easier. So if you have like, if we put it on Wednesday and you're like, I have 3 exams Wednesday, that's silly. Just email me. Like literally just email me and we can work something out. It's not that hard. We can do it. So just let me know. But if you don't talk to me, I can't help you. So, okay. Cool. Where is it? Sorry, I'm just trying to get my, okay, cool. Found it. Okay, so, ooh, okay. I think today that we're going to talk about continuous cooling diagrams, and continuous cooling diagrams for steel. And then we're going to transition back to polymers and ceramics and talk broadly about, you know, the three main groups in this course, which are ceramics, polymers, and metals. And then we can discuss them, how they're the same, how they're different, why they're the same, why they're different, stuff like that. Because I think that you should be comfortable with those ideas. Okay, so, but to start, let's discuss cooling. So, yeah. Okay, so let me quickly okay, so this is the outline of our carbon ion steel phase diagram. Here we have weight percent carbon in iron, right? Here we have temperature. This diamond shape, we have austenite. Here is the alpha ferrite. Here's delta. This is the liquid phase. This line indicates 6.3 weight percent carbon, right? And that is, beyond that, we have, cast iron. So we're only walking from 0 to 6.5. And, these are all phases of, or regions of two phases. So here we have ferrite plus cementite, austenite plus cementite, austenite plus the liquid phase, ferrite plus austenite, something like that. Okay, so and so when we make our alloy, we mix our composition together, we heat it up. So we will start at some point on this graph, maybe here, right? And then we will cool it, the metal down to room temperature, to the temperature of humans, somewhere down here. And we discussed on how if we cool the temperature in different ways, if we cool the material in different ways, we can get different crystal structures. So one thing, if we cool it really fast, if we quench it, we kind of freeze the atoms in place. And that's the way to preserve the austenite crystal structure at lower temperatures. But quenching is actually rather hard, and it's hard to do on a large scale, right? Because if you're trying to build a big beam, it's kind of going to be hard. So instead, humans are lazy, right? So we're always trying to do the easiest thing. And so the easiest thing is to just take it out of the oven, right? You just take it out of the oven and you put it in a room, right? And that room has a temperature. And so essentially what we're doing is we're taking something hot and we're putting it in a constant temperature environment. So we're cooling it, at a constant temperature. And then we're just seeing what happens. We're just seeing how the microstructure changes over time. And so it will just decrease, slowly decrease, right? And then it will form two phases, and then eventually it will form the ferrite and cementite phase, right? And so that we call pearlite, because it's going to be, we talked about how it's going to be the striped bands of ferrite and cementite, right? The pearlite phase. And so we have these two ideas of the temperature at which we put the thing in and the time at which it takes to get to that temperature. And so from there we can adapt this phase diagram to instead of describing phases as a function of composition and temperature, then to just describe phases as a function of temperature and time. And so that looks like something like this. I really messed that up, didn't I? Okay. Oh, wet. That's good. Okay, so yes, now we're going to have temperature here. And then we're going to have time here. And we're going to make this the same phase diagram, but just instead of composition, we're at a set composition, right? So we're traveling along that line in the phase diagram. And, so the first thing we can do is draw this temperature up here. This is the eutectic temperature. And this is the temperature where the austenite phase meets the alpha plus cementite phase, right? So above this temperature, we have all austenite in this case. So we're going to write an A here for austenite. And as we begin to cool the material, right, we're going to continue to have austenite initially after we cross this threshold. But there will be a point where we will start to have a conversion of phase, right? And that looks something like this, where we would start to have a, we will have a threshold where we cross this boundary and start to form pearlite. And so this first diagram denotes the beginning of this reaction. We're starting to form pearlite, right? So this is 0% formation. And this curve, we will say, is 100% formation. And then so if we ever end up at a higher temperature, at a high temperature at this time, we will form the pearlite phase, which is the striped microstructure. And so typically what happens is we start up here, we open the oven, and the alloy cools very slowly. We cross the eutectic temperature, we're doing well. We cross this band, and now the phase transformation has actually begun. The phase transformation has actually begun. And once we've crossed this band, now we're fully 100% formed the pearlite microstructure, and it will just continue to cool in that way. The other thing that could happen is that if we cool a little bit quicker, right? Or let me do it like this. Like this, if we cool now, we're just cooling at a quicker rate. So that could be putting it in a colder oven or a colder environment. We will form bainite. Now, bainite is very similar to, bainite is similar to perlite, but it's slightly different because so bainite is slightly different from perlite because the bands are not as pronounced. So while in perlite we have these nice, we have these nice striped patterns that occur. In bainite, we cooled it faster. So the stripes look something more like this. Right, so the space separation has occurred, but it's not as uniform because it was a faster process. And in that way, we've really it's a bit of a nuanced distinction between these two, but it's a distinction nonetheless. And then the last thing we do is if we cool so quickly, we completely bypass this nose, right? We don't even really engage. We don't pass this threshold at all. That's basically taking something really hot and quenching it. We will freeze the atom, essentially freeze the atoms in place, and in that way, we'll form a disordered structure. Some people like to call these metallic glasses if they're trying to be fancy. But in the case of steel, this is called martensite. And so what is important to note is that this nose, like this time, okay, so what is this time, right? So this time could be like 1 second, like literally 1 second, and then this might be 10, this might be 100, 1,000. So this really happens. Oftentimes you'll see these graphs plotted in a log scale or an exponential scale or some type of scale that compresses time because or this denotes time in a nonlinear way. Because to form martensite, it's not impossible, but you have to be very quick. You have to really cool the material very quickly because it's a high stress state and atoms will not remain in that stress state for a very long time. So these this is called the continuous cooling diagram. And the one thing about it that is interesting is how these diagrams are made, right? So you see this? Is this okay? So what I'm going to do is now I'm going to demonstrate how we make these diagrams. And in that way, I hope to reinforce the interpretation of them. So what we can do is track the phase transformation over time, like we did previously. So in the beginning, there was the nucleation period, right, where no phase transformation is occurring. And then we will get, and then very rapidly, we'll get the phase transformation to occur. And then we can repeat this. And so then we can denote important metrics of time. So this is 0%, this is 100%, and this is 50%, right? And then now we track the conversion over time, and we can now plot that on our temperature versus time graph. So, okay, at this temperature, we had 0, 50, 100. We can now repeat it at different temperatures. So maybe if we go to a different temperature, it's like this, 0, 50, 100. Like this. And now maybe we go to a different temperature, it's like that. 0, 50, 100. And now we've done this experiment at theta. What is the y-axis? Yeah, so that's sorry. So this is time is the x-axis, and the y-axis is the percent conversion of the reaction. So what we're doing on top is we're taking the sample and putting it at a constant temperature and tracking the conversion over time. And now we're plotting these on the time versus temperature graph, the 0, 50, 100%. And now we're just going to connect the curves like this. So I really just remade the graph we just discussed, but I should have done this first, to be honest, because I was describing how we, how we derive this graph. And so the continuous cooling temperature graph, right? So and now we have austenite here, perlite, bainite, and martensite down here. So previously, when we discussed this, when we introduced this graph, we were just saying what happens when we cool at a constant rate, right? But this graph is also a lot more powerful than that, because we can also do many different types of cooling situations we wanted. So we could cool at a constant rate, and once we reach 50%, we could crunch the material very quickly. And in that way, we can target a 50% perlite composition, or a select, or maybe we want a different type of microstructure. We can traverse this graph accordingly. But I just wanted to reiterate how this graph was formed. And that's why I introduced the time versus conversion graphs above. And so, yeah, so these graphs are unique for each composition of your alloy. So if you're looking at different compositions of steel, you would have to recreate these experiments multiple times. So some poor soul has done all of these steel cooling experiments, so we don't have to. Okay. Cool. So I think this is in chapter 10 in the book. So chapters 10.5 and 10.6, we would do a good job of describing these graphs. And I hope that everyone is comfortable with these topics, for the next upcoming weeks or so as we continue on our way. And the last thing I wanted to discuss or rediscuss really is this idea of ceramics and polymers. I know the recent lectures have been discussing ceramics and polymers and having described them. So ceramics, so just like how in the first exam we discussed how metals can be processed to increase their strength, it might be interesting to also learn how ceramics and polymers can have their strengths or physical properties modified. So if we revisit stress and strain, right? If we revisit the stress strain curves, we can draw stress strain for a metal. This. So this is a metal. Right? We very clearly have the linear region, and then we have the plastic deformation region. This is a ceramic. A much higher elastic region, very tiny plastic region. And the last thing we have is a polymer. Very short elastic deformation, very long exaggerated plastic deformation. And we discussed for metals, cold walking, precipitation, grain hardening, whatever. We've discussed all of those ways we could do that for metals. And really we could do that because metallic bonds are so interesting. Metallic bonds are so unique in how they operate, and the dislocations form such a big role. Right, but polymers are long chains of repeating units, and they form crystals, but they're not always 100% crystalline or 100% amorphous. There's always this in between. So the ways that we can strengthen polymers, the ways that rather we can strengthen metals, we can't really directly apply to polymers, or we can't apply them directly to ceramics. So I think ceramics and metals have a lot more in common than polymers do with these either groups. So when we have one way we can increase polymer strength is through this process called cross-linking, right? So if these are all polymer chains, right? Something like this, right? Oops. So as you pull on the chains, they will elongate, right? And the strength from polymers really comes with the chains catching on each other. So if you have like one chain that goes this way and the other chain goes this way, they're caught on each other, and that's what gives us our strength. But that's not a very sound method, and that's why the strength is so low, because they just they would just slide right past each other, introducing permanent plastic deformation. So one way we can combat that is by physically bonding the polymer chains together in a process called cross-linking. So if I connect these two chains, or these two chains, or these two chains, or these two chains, now we're getting more of a net-like structure instead of a plate of spaghetti, right? Like, so as we're forming the net, now when you pull on one strand, you have to pull on all the strands, right? And so that in that way, it increases the strength of the material. Like that. And just like in code walking, it may increase the strength of the material at the sacrifice of some plastic deformation. So So there's always a give and take between these two approaches. And oftentimes to get a stronger elastic modulus, we have to sacrifice some of our plastic strain. Another way we can really influence polymer performance is, temperature and the rate in which we pool. So if we put something at a very small temperature, low temperature, we restrict movement of atoms, we restrict diffusion, right? And so as a result, we'll get a very short region of plastic deformation, right? T1. And as we increase, the temperature, right? As we increase the temperature, it becomes hotter and higher and higher, easier for atoms to move, and as a result, we get more plastic deformation. But then eventually, we might increase the temperature so high that we melt the plastic, and that's not good. Don't melt, right? So again, there's an upper and lower bound to this. And likewise, the rate at which we pool becomes very important for polymers. So if you apply the stress all at once, this diagram doesn't account for time, and time's always like the third variable. So if we pool very fast, like this, we're probably going to get a very quick brittle break. But if we pool very slowly and we apply this stress out fairly gradually, we will give every chain the ample opportunity to respond to the stress and to deform and move accordingly. And as a result, we'll have very nice, long plastic deformation. So oftentimes, we don't even have to do anything to the structure itself. We just test the material slightly differently, and we can get our desired performance. So this idea of temperature dependence harkens back to a couple of weeks ago when we discussed glass transition temperature. So I would advise everyone to review glass transition temperature. I have to post the video, so I will post the video again. And so glass transition temperature exists both in polymers and in ceramics. And I hope everyone could take the time to review that, learn the concept, and learn how they are similar and different in ceramics and polymers. And then next week, we can take the time to discuss that. Other than that, I think that is pretty comprehensive for today. Again, if for the exam one, let me know if you want to review your exam. When I grade, I give everyone a little note sheet. So if you get graded by me, you would get a little table. Some people might not do that. So if you want one, I'll be more than happy to do that for you. Okay. And then exam 2 is looking like it's going to be from the 19th to the 24th. Similar length, similar style questions. I hope everyone found it agreeable, and then I will also get back to you about the final exam and the time of that, the timing of the final exam. Okay, so have a great day, everyone. I will talk to you later. Bye-bye.